Welcome back to the deep dive. Today we're tackling something that's, well, fundamentally reshaping how we think about digital security. If you are involved in building, buying, or even just relying on large language models, maybe it's an internal chatbot, maybe something much more complex like an AI agent. These things are powerful, transformative even, but here's the rub. They also bring a whole new set of risks. We're talking about a shift away from systems we could predict, systems that were deterministic, into a world governed by, well, probabilities.
That shift is absolutely the core issue here. I mean, traditional cybersecurity, it was built for finding specific bugs in code, right? Fixing flawed access controls, things you could pinpoint. But when the engine itself is probabilistic, that old framework starts to buckle. We're facing, entirely new attack vectors, things like prompt injection, basically tricking the AI, or these subtle membership inference attacks that can leak the very data the model is trained on. The old security playbooks, they just don't cut it anymore.
Exactly. And that's why we're diving deep into a really significant piece of guidance today. Our source material is the brand new and frankly incredibly detailed Guidelines for Penetration Tests of Large Language Models, or LLMs.
Yeah, this document is a big deal. It provides the kind of structure the industry has really been needing. We're talking 98 pages, version 1.0, dated September 24th, 2025. And importantly, it's from the KI Sycarite Expert Circle. This isn't just theory. The authors are from major players: Sequire Technology, Blackford, Roche Rechtsanwaltsgesellschaft, DCSO, RT-Solutions.de, and significantly, the German Federal Office for Information Security, the BSI. This is aiming to be the standard for how we secure these critical AI systems.
So our mission today is to unpack this framework piece by piece. We want to give you, our listener, a really clear, structured understanding. How do you actually plan one of these tests? How do you commission it? What goes into executing a specialized LLM penetration test? It's all about bringing some uniformity, some consistency, and maybe most importantly for anyone auditing or paying for these tests, comparability. If you follow this guide, you should know what level of security assurance you're actually getting.
And let's be really clear about who needs this. If you're an IT security officer trying to budget for this stuff, absolutely essential. Development teams, you need to build security in from the start, and this shows how. Auditors, reviewers, validating these systems. Indispensable. The guide really hammers this home. We're moving beyond classic IT security. We have to grapple with this unique probabilistic nature of LLMs. And, the uncomfortable truth is that the uncertainty around finding all the vulnerabilities, it's just going to be higher than with traditional software. We have to accept that and plan for it.
Okay, let's get into it then, starting right at the beginning, Chapter 1. Before we can even talk about how to test, the guide very wisely says, look, we need a shared language. We need to agree on the terms.
Absolute fundamental. Can't talk strategy without the same dictionary, right? So, top level, large language models, LLMs. These are AI models, usually that transformer architecture you hear about. Their power comes from scale. Billions of parameters, trained on truly massive amounts of text. That's how they learn human language patterns, how they understand and generate text. Think GPT, BERT, those families.
And when the guidelines mention LLM integrated applications, what exactly does that cover?
That's basically any software system that uses one or more of these LLMs to do some of its work. Some part of its processing logic relies on the LLM and the integration point, where the model meets the rest of the application. That's where, honestly, most of the new risks pop up.
Right, the connections. Let's talk about some systemic issues then, things like bias.
Yeah, crucial and often underestimated until something goes wrong publicly. So bias is any systematic distortion in what the model puts out. Usually it comes from the training data being unbalanced or, frankly, reflecting historical biases. Then you have bias propagation. That's where the model's bias doesn't just stay in the model, it gets amplified. It gets passed down to other systems or used in decisions, and suddenly you're automating discrimination in things like hiring or loan applications.
Right.
It's a serious problem.
Okay, now for the output itself. We hear hallucination all the time, but the guide actually makes a distinction. Hallucination versus confabulation. What's the practical difference there? If I'm a developer, why should I care about that distinction?
It's hugely important for fixing the problem. A hallucination is when the LLM just makes stuff up. It sounds plausible, maybe, but it's factually wrong, totally disconnected from its training data or the input you gave it. Pure invention. Confabulation, though, is different. It's still false content, but it seems logically connected. It often comes from the model misinterpreting or overgeneralizing patterns it saw in the training data. There's a kind of faulty logic trail back to the data, even if the conclusion is wrong.
Okay. So if I see a hallucination, maybe I just need tighter output rules, some stricter guardrails, but confabulation might mean I need to look at how my Argy system is pulling context, or even rethink the data the model learned from.
Precisely. One points to output control, the other points potentially deeper to input, context interpretation, maybe even the core training. Understanding that difference tells you where to start digging. Okay, let's switch to the adversarial side. The developer tries to control the LM's behavior using the system prompt. That's the set of instructions, the rules saying be helpful, don't say harmful things, stay on topic, etc.
And the most famous way to break those rules is prompt injection. That's where the user writes a clever prompt that basically overrides the system prompt, right? Makes the model do something it wasn't supposed to.
Exactly, it's the classic attack. But then there's the sneakier version, indirect prompt injection. Here, the attack isn't in the user's direct chat message. It's hidden in third-party content. Maybe a document someone uploads or a web page the model retrieves using R, or even a malicious email it processes. The LLM reads this external data, misinterprets part of the data as a new instruction, and that overrides the original system prompt. It's much harder to detect because the attack comes through the data pipeline.
Nasty. And what about the term jailbreak? How is that different?
A jailbreak is a specific kind of adversarial prompt. The goal is usually more extreme, to make the model completely abandon its safety training, its ethical guardrails. You're trying to force it to generate content. It was explicitly designed not to generate maybe illegal instructions, hate speech, that kind of thing. It's about breaking the fundamental safety constraints.
Okay, got it. And to wrap up the definitions, the guide stresses that security isn't just technical fixes. It brings in data governance and AI governance.
Yes, and this is critical. Governance is the whole framework around managing data quality, security, compliance. For LLMs, this means you can't just focus on technical defenses like filtering prompts. You also have to consider the impact on the organization, on the users, the ethical dimensions. Strong governance is about managing the entire risk picture, technical and societal, that comes with these autonomous systems.
So the guide makes a really strong point that the risk often isn't just in the LLM model itself sitting in isolation. It's amplified by how it's deployed, where it lives, and especially how it's integrated, how it connects to everything else. We need to look at both.
Absolutely. Let's start with where the deployment forms. The security implications change dramatically depending on the infrastructure.
The first couple are probably what most people use commercially.
Right. You've got public cloud service. That's shared infrastructure, like using a big provider's standard API. Conditions vary, maybe free or paid tiers, and you're subject to their data handling rules. You have limited control. Then a step up in control is dedicated software as a service, SaaS. Here, the LLM runs on resources specifically for you, logically separated from other customers. This means stricter data separation, usually better guarantees on performance and availability. More control, more cost.
Okay, then there are options where you, the customer, manage the model more directly, even if not the bare metal.
It's exactly infrastructure or platform as a service. Here, the provider gives you the specialized hardware, maybe GPUs, and the environment to run the LLM. But you bring your own model, maybe one you trained or an open source one. The model's security responsibility shifts heavily to you. Then there's central on-premises installations. Your organization provides and manages everything, the specialized hardware, the environment, the model. Full control, but also full responsibility for absolutely everything, including physical security. And finally, the really cutting-edge stuff, edge installations. Think smaller LLMs running directly on laptops, smartphones, IoT devices, even industrial controllers. This massively decentralizes the attack surface. Suddenly, the security of every single endpoint becomes critical.
Okay, that covers the where. Now for the how the integration forms. You said this is where risks multiply.
They really do, because this is where the LLM touches your organization's valuable data and processes. It's almost always via an API, but it's the application logic around that API that creates the danger zones. You might have a simple chat interface, maybe just for internal testing, but the complex chat interface is more common for real use. That usually includes things like user management, who can access what, chat history, persistence, and crucially, the ability to upload documents as context. Think about that users are feeding files directly into the model's context window. Those files could be internal reports, sensitive data, or cleverly disguised prompts for an indirect injection attack.
So the inputs are risky, but what about the outputs and connections? The guide mentions tools, Workstudge. What are those?
Tools are basically external functions the LLM can decide to call. Think of giving the LLM the ability to query a database, call another API, maybe check inventory, or even execute a script. The LLM gets a description of the tool, and based on your prompt, it decides autonomously, okay, to answer this, I need to use the database query tool. Here's the massive risk. What if that external tool itself has a vulnerability? A standard bug, like not sanitizing its inputs properly. Now, a user crafts a cron conjecture attack. The LLM, trying to be helpful, takes that malicious input and passes it as a parameter to the vulnerable tool. Suddenly, your text-based attack on the LLM becomes a code execution attack or a SQL injection attack on the system the tool connects to. The LLM acts as the interpreter that bypasses the tool's own defenses.
Wow, okay, that's a serious escalation path. What about when the LLM writes its own code? Code generation and execution.
Yeah, another powerful but risky integration. Sometimes, the easiest way for an LLM to solve a problem, like a complex calculation, is to write a little snippet of code, say in Python, and then run it. This must happen in a very secure, isolated sandbox. If that isolation is insufficient, the code the LLM generates could potentially escape the sandbox. It could read files on the host system, change configurations, connect to internal networks. Essentially, you've tricked the LLM into writing and running malware on its own host.
And the integration that really unlocked a lot of the practical use cases, but also risks. Retrieval Augmented Generation, or RAG.
RAG is everywhere now. It's fundamental. The idea is to give the LLM access to external up-to-date knowledge. You connect it to your document databases, internal wikis, maybe even live web search results. When you ask a question, the RAG system first retrieves relevant documents, adds them to the prompt as context, and then the LLM generates the answer based on both your question and that retrieved context. This makes answers much more accurate and relevant. But it introduces huge risks. That external data is now effectively part of the LLM's instructions for that turn. This opens the door to data poisoning. If an attacker can place malicious instructions within one of those retrieved documents, the LLM might execute them. That's indirect prompt injection via the knowledge base.
So the data source itself becomes an attack vector. Are there other RAG risks?
Absolutely. Think about access control. The RAG system retrieves documents based on relevance to the query. But does it also check if the specific user asking the question actually has permission to see the contents of those documents? If not, insufficient access controls, the RAG system might pull a highly sensitive document, feed it to the LLM as context, and the LLM then happily summarizes or answers questions based on that sensitive data in its response to the user. The user just bypassed the standard file permissions through the LLM.
Okay, beyond direct data interaction, there are risks in just managing these complex systems, right? Like LLM routers.
Yes, managing complexity introduces its own failure modes. An LLM router is a clever idea. You have multiple LLMs available, maybe a small, fast, cheap one for simple questions, and a big, powerful, expensive one for complex reasoning. The router looks at the incoming query and decides which LLM to send it to, optimizing for cost and quality, the risk. If the routing logic itself can be manipulated or has flaws, an attacker might craft a query that looks simple, so it gets sent to the cheap, maybe less secure model. But the query is actually designed to extract sensitive data that only the big model should handle. Or maybe they trick the router into sending millions of queries to the expensive model, running up huge costs, a denial of wallet attack.
And orchestrating multiple steps, chaining and workflows.
Right. Sometimes you need multiple LLMs, or an LLM plus other tools working in a sequence. Output from step 1 feeds into step 2, and so on. A workflow. The risk here is error propagation. If an LLM early in the chain hallucinates, gets injected, or produces wrongly formatted output, that error can cascade down the entire chain, potentially corrupting data or causing the whole process to fail unpredictably. The failure point might be far removed from the initial error.
Which leads us to the systems where the LLM is really in charge, agent systems. What makes securing these so much harder?
Agent systems are a major step up in autonomy. Here, the LLM isn't just answering questions. It's acting as a coordinator. It takes a complex goal, breaks it down into steps, and then autonomously decides which tools or other LLMs to call in what order to achieve the goal. But control flow isn't fixed. It's dynamic, decided by the LLM itself based on the situation. An attack here isn't just about getting a bad answer. A successful prompt injection could potentially make the agent trigger a whole sequence of unintended, harmful actions across your network using its delegated authorities. And because it's autonomous, it might happen without any human noticing until it's too late.
And the guide even looks at the ultimate endpoint, cyber-physical agent systems.
Yeah, this is where the digital meets the physical world directly. These are agent systems that can interact with and control things in the real world. Think industrial robots, autonomous vehicles, smart building controls. The potential damage here shifts dramatically. It's no longer just about data breaches or financial loss. A compromised cyber-physical agent could cause actual physical harm, damage equipment, or disrupt critical infrastructure. We're crossing a very serious threshold here in terms of security impact.
Okay, it's crystal clear from all that Traditional pen testing methods just aren't going to cut it for this level of complexity and, frankly, weirdness. Why exactly does this guide insist on a separate, specialized methodology for LLM pen testing? What's the absolute core difference?
The non-negotiable fundamental difference is the non-deterministic behavior. Classic pen tests, they target systems that are deterministic. You put in a specific input, you expect a specific output. If you send a specific SQL injection string, you expect the same database error every single time, right? With an LLM. Forget it. You can send the exact same prompt 5 times and get 5 slightly different answers. Small, almost meaningless changes to the prompt wording can lead to wildly different, unpredictable, and potentially dangerous results. It's operating on probability, not fixed logic.
So you're not just looking for a single failure instance. You're trying to figure out the likelihood of failure. How does that change how you actually validate a vulnerability in practice during a test?
It completely changes the validation process. You can't just say, aha, this prompt injection worked once, vulnerability found. That's not enough. The testers have to run variations, sometimes hundreds, even thousands, of subtly different versions of an attack prompt. They need to measure how often the attack succeeds in bypassing the guardrails. The report won't just say, system vulnerable to prompt injection. It'll say something like, using technique X, we were able to bypass the content filter in 18% of attempts across 500 variations, indicating a significant weakness in robustness against this attack class. It's about statistical significance and probability of failure, not just a single yes-no result. That's unique to LLM testing.
Given that probabilistic nature, what does this guide define as the specific scope of a proper LLM pen test? What's in, what's out?
The scope has to be quite focused to be manageable and meaningful. It primarily targets vulnerabilities that arise directly from the use or the process control of the LLM within the application. So that includes 1. Technical security things like adversarial attacks, prompt injection jailbreaks, APS security flaws. 2. Data-related risks, leakage of training data, leakage of sensitive input data. 3. Content and ethical aspects testing for harmful content generation, bias, hallucinations. And 4. Regulatory requirements demonstrating compliance where needed. It's about the LLM and its application context.
And equally important, what needs to be explicitly left out to keep the test focused and practical?
Right. You can't boil the ocean. So generally excluded is standard, traditional IT security stuff, physical security of the data center, basic network firewall configurations, standard vulnerability scanning of the host OS. That's covered by other tests. Also, typically excluded is a deep audit of the foundational model's architecture or the original massive training dataset sources. Why? Because often the organization using the LLM didn't train it and doesn't have deep visibility or control over that. It's often a third-party model. And critically, you cannot test every single possible way someone might interact with the LM. It's infinite. The test must focus on the defined scope, the key use cases, and the identified high-risk integration points. Keeping it focused is key to getting actionable results. Okay, let's shift gears a bit and think about the why from an organizational perspective. If you're the CISO, the IT security officer listening to this, why should you carve out budget for this specialized testing? It sounds like it goes way beyond the usual annual pen test. It really does, and frankly, it's becoming non-negotiable. It's a strategic investment. First, it's about ensuring robust security and trust. These LLMs are increasingly handling your crown jewels, sensitive customer data, proprietary information. You need to find those vulnerabilities, those potential confidentiality breaches before an attacker does. The cost of a major LLM-related breach could be astronomical compared to the testing cost.
And it's not just about data leaks, right? It's about the reliability of the system itself, especially if it's making automated decisions.
Absolutely. Maintaining integrity and performance is critical. Imagine your business relies on an LLM for dynamic pricing or for critical anomaly detection in an industrial process. If that LLM can be manipulated to give wrong answers, or if it can be taken down by some attack, your core business operations could grind to a halt or make disastrously wrong decisions. Testing verifies it's reliable, even under attack.
And then there's the regulatory hammer.
You can't ignore compliance. Especially in Europe, with the AI Act and other regulations coming online, you will need to demonstrate that your AI systems, particularly high-risk ones, are secure and robust. These specialized LLM pen tests generate the concrete, auditable evidence you need to provide to regulators. And doing this also helps build stakeholder trust, being able to show customers, partners, regulators that you've done this rigorous, transparent testing. That builds confidence that your AI is safe and reliable. It's moving from a necessary evil to a strategic differentiator. #2.2 requirements for the testers.
Profende. So, if the risks are so different, it follows that the people doing the testing need a different skill set than your average network pen tester. What kind of expertise does the guide say these LLM testers absolutely must have?
Yeah, the guide is very clear. This is specialized work. You need testers with a deep, current understanding of a few key areas. First, model architecture. They need to understand how models like GPT and BERT actually work internally, not just how to use their APIs. What are attention mechanisms? How does context windowing affect security? Second, common attack techniques. They need to be masters of the LLM-specific attacks, crafting sophisticated adversarial inputs, advanced prompt injection strategies, techniques for extracting training data or model parameters. This is a rapidly evolving field. And third, critically, ethical aspects and legal compliance. The testers themselves have to operate ethically and legally. They need to design tests that don't inadvertently cause real harm, leak excessive data, or generate genuinely dangerous content. They need to understand the legal boundaries, especially around data privacy. It's a blend of deep technical skill and ethical awareness. Security expert meets AI expert, hashtag 3.1, 3.6, technical scope and execution.
All right, let's get practical. Before a single test prompt is fired, there's a lot of technical groundwork and agreement needed between the client and the testing team, setting the stage correctly.
Absolutely. 3.1, defining the test object, proof object, is step one. You have to clearly delineate what's actually being tested. The guide breaks it into three main areas. First, the model itself, maybe looking at its known properties, potential biases based on its training data description, any accessible hyperparameters. Second, the API interfaces. How does the application talk to the model? Authentication, rate limiting, input validation at the API layer are key attack surfaces. Third, input mechanisms. How does user input or external data actually get to the model? Web forms, document uploads, RIG databases, email parsers, all potential entry points for attacks.
And once you know what you're testing, you need to define how deep you're going. 3.2 test depth. Proof.
Right. This needs explicit agreement upfront. Are the testers working black box, meaning they have zero internal knowledge, just interacting like a regular user? Or white box, they get full access to source code, architecture diagrams, maybe even model weights? Or the common middle ground, gray box, they get some internal information, maybe API specs or high-level architecture, to help guide their external testing. The depth drastically affects the time, cost, and type of vulnerabilities you're likely to find.
Then basic logistics. 3.3 test location, proof ort, and 3.4 test period, proof site trom.
Seems simple, but important. Where is the system hosted? Testing an in-house system versus a cloud-based size requires different approaches, different permissions, and the timing test period needs defining. Is it a one-off test or part of a recurring cycle? And crucially, when will the tests run? Almost always, this should be scheduled outside of peak business hours to minimize any risk of disrupting live operations. Testing production systems directly is generally a bad idea unless there's explicit, high-level sign-off and strong legal protections in place.
Okay, and 3.5 test conditions, Prüfbedingungen, sounds like it's about ensuring the testing is done responsibly.
Exactly. This covers things like what specific access rights do the testers need, and how will they be securely provisioned and revoked? Critically, will they use synthetic or anonymized data wherever possible to avoid risks to real personal data? Are the testing tools themselves secure? And there's a strong emphasis on detailed documentation during the test logging, all actions, prompts, and results for accountability and reproducibility.
Which leads nicely into the client's homework, 3.6 documentation. What information does the client need to provide to the testers for them to do their job effectively?
For a proper deep dive, the testers need good information. The guide specifies things like diagrams of the application architecture, showing how the LLM integrates, descriptions of the training data sources, especially if there are privacy implications, detailed documentation for any APIs involved, and the security concepts already in place for user interaction and data handling. Without this baseline info, the testers are essentially fumbling in the dark on some of the most critical integration risks. Okay, this next section is absolutely critical, and it's not technical, but it underpins everything. Legal prerequisites. Look, penetration testing, by its nature, involves doing things that could look like unauthorized access or interference if you don't have explicit permission. So the guideline is emphatic. Clear, written legal agreements are mandatory before any testing starts. No exceptions.
Right, and the core of that is the explicit written consent. The guide calls it the rules of engagement, or Fragebierklärung, what absolutely must be nailed down in this document, especially given how sensitive LLMs can be.
It needs surgical precision. You need to define the exact scope. What systems, what IP addresses, what functionalities are in scope. Equally important, what is explicitly out of scope. For example, Prompt injection against the customer service chatbot API is allowed, but attempting to access the underlying customer database via that API is forbidden. You need the precise test period, exact start and end dates and times. Permissible methods. Are denial of service attempts allowed? What about data exfiltration tests? Social engineering, it needs to be spelled out. Then huge ones. Liability and risks. If the test inadvertently causes downtime or data corruption, who is responsible? Are there limits on liability? What about unexpected cloud costs if a test runs away? And absolutely vital for LLMs, confidentiality and data protection. How will any sensitive data encountered during the test be handled? This almost always requires non-disclosure agreements, NDAs, and potentially formal data processing agreements, DPAs or CPAs under GDPR.
The guide makes a point of highlighting the current legal uncertainty. It even mentions a potential Strafbarkeitsrisiko risk of criminal liability under German law if you test without that explicit consent. Wait, so even if I'm doing an internal test, just trying to secure my own system, if I touch employee data or use certain aggressive techniques without that super specific documented permission, the testing itself could be illegal. That seems extreme.
It is a significant point of concern, and the guideline flags it explicitly, referencing specific paragraphs in the German Criminal Code, StGB. The issue is that certain testing techniques could be interpreted as unauthorized data access or system interference. Even for internal teams testing their own systems, if they probe too deeply without the right authorizations, especially involving employee or customer personal data, they could theoretically cross a legal line. Experts are definitely calling for clearer legal safe harbors for legitimate security research and testing. But until those exist, that signed, detailed rules of engagement document is the organization's crucial legal shield. Get the data protection officer involved early.
And all this internal legal pressure is amplified by the big wave of EU regulations that are increasingly mandating this kind of testing, right? Let's connect the dots. How does doing these LLM pen tests help meet compliance for things like the AI Act?
The AI Act is probably the most direct driver right now, especially for systems classified as high-risk AI systems. Think critical infrastructure, medical devices, law enforcement tools, the areas listed in Annex 3. Article 15 of the Act demands high standards for accuracy, robustness, and cybersecurity for these systems. Well, how do you prove robustness and cybersecurity? A specialized LLM penetration test is the most concrete way. You can't just claim your system resists prompt injection. You need a test report showing you tried sophisticated attacks and it held up. The pen test provides that critical evidence for your conformity assessment.
And beyond just AI systems, there's broader critical infrastructure resilience.
Exactly. That brings in the NIS2 directive. This applies to a wide range of essential and important entities across many sectors. It requires them to implement strong cybersecurity risk management measures and, crucially, procedures to assess the effectiveness of those measures. Penetration testing is a primary method for assessing effectiveness. The LLM Pentest report becomes key documentation to show NIS2 auditors that you've validated the security of your AI components.
And the financial sector has its own specific rules with DORA.
Right. The DORA, Digital Operational Resilience Act, imposes very demanding requirements on financial institutions for continuous and comprehensive resilience testing. Since banks, insurers, and investment firms are rapidly adopting LLMs for everything from fraud detection to customer interaction to algorithmic trading support, pen testing these LLM integrations becomes a central, unavoidable requirement under DORA to demonstrate their operational resilience.
What about manufacturers of products, the Cyber Resilience Act?
Yes, the Cyber Resilience Act, CRA, is coming into effect around December 2027. It mandates that manufacturers of products with digital elements, which explicitly includes many AI systems, especially high-risk ones, must ensure and demonstrate security throughout the product's lifecycle. This includes regular and effective security testing after the product is on the market. The AI Act and CRA are closely linked here. Meeting the AI Act's cybersecurity requirements, often proven via pen testing, will be a key part of fulfilling the CRA's obligations for ongoing security validation.
And finally, the bedrock of data protection, DSGVO-GDPR. How does LLM pen testing fit there?
GDPR is always in play whenever personal data is processed, which is very common for LLMs, customer service chats, document summaries, etc. Article 32 of GDPR requires appropriate technical and organizational measures to ensure the security of personal data processing, confidentiality, integrity, availability, resilience. An LLM penetration test provides tangible, auditable proof that you've implemented and tested appropriate technical measures. It specifically helps demonstrate resilience against attacks that could leak personal data, like information leakage A6.1.2, or compromise its integrity. It helps fulfill that core accountability principle of GDPR.
Okay, so we've covered the why, the what, the who, and the crucial legal framework. Now let's get into the how. The guide lays out a standardized four-phase workflow for actually conducting an LLM penetration test. This structure is key for making the results consistent and useful. Hashtag 5.1 business understanding and initial unclass.
Right. Phase one is all about understanding the context. Before any technical testing happens, you need this business understanding and initial analysis, or IST-analyses. It's basically an intense dialogue phase. You have to clarify the timeline. How long do we actually have for this test? And the budget scoping. What level of depth is feasible given the resources? These practical constraints shape everything that follows.
So the testers almost have to act like consultants or business analysts at this stage, really understanding the client's goals and limits.
They absolutely do. They need to figure out the level of support they'll get from the client who's the main contact, what internal documentation will be shared. They also need to pin down the test environment. Ideally, this is a dedicated staging or QA environment that mirrors production. Testing directly on production is highly risky and needs that explicit sign-off we talked about, and maybe the most crucial part of this phase, thoroughly going through the detailed questionnaire provided in Appendix A5 of the guide. This questionnaire is designed to capture all the specifics, the exact use cases, the compliance needs, which LLM models are involved, the deployment environment, specific integrations like RE or tools. Given the complexity, this deep information gathering upfront is non-negotiable for planning an effective test. Hashtag 5.2 threat modeling, prioritization, and test planning.
Okay, so once all that information is gathered from the analysis phase, the preparation shifts into building an actual test strategy. How does the threat modeling part adapt specifically for LLMs?
The team will use established threat modeling techniques, like maybe Stride or AT&CK for cloud, but they apply it with an LLM-specific lens. The focus shifts a bit. It's less about just finding traditional software flaws and more about modeling the potential impacts of the LLM's unique failure modes, its non-determinism, its potential for manipulation through prompts. You're modeling against unpredictability as much as against known vulnerabilities.
Can you give a couple of examples from the guide of the specific LLM threats they'd be modeling against in this phase?
Sure. The guide in Appendix A 1.1 lists things like spoofing, maybe tricking API authentication, or impersonating a legitimate user to the LLM. Tampering, manipulating input data, using adversarial techniques the model might misinterpret. The big one, prompt injection in all its forms. Data extraction, trying to coax the model into revealing sensitive training data or secrets it learned. Even things like training data poisoning, where the threat actor might have tried to influence the model before the test by inserting malicious data during its training phase. And model distillation attacks, trying to steal the model's capabilities by observing his inputs and outputs.
So once those potential threats are mapped out, how does the team decide what to actually test within the time and budget constraints?
That's where the planning gets concrete. It links directly back to that detailed questionnaire from Phase 1. The guide, Appendix A 5.2, actually helps map the client's specific functional choices, like, are you using external tools, or do you employ RGRE, directly to the relevant risk scenarios in Appendix A6. Based on this mapping, the testers prioritize. They focus on the threats deemed highest risk, likelihood times impact, for this specific application, and which can realistically be tested within the agreed scope and budget. You can't test everything, so prioritization is key. This is also the stage where the client must provide the required access and information agreed upon earlier. Things like architecture diagrams, descriptions of training data sources for privacy risk assessment, API documentation, and the necessary user accounts or permissions for the test environment. Hashtag 5.3, testing and documentation.
Phase 3, execution time. Given the challenges we discussed, especially the non-determinism, what does the guideline emphasize during the actual testing and documentation phase to make sure the results are valid and useful?
The execution follows the prioritized plan, focusing on testing the system's robustness against those specific targeted attacks. But because results can vary, the documentation during this phase has to be absolutely meticulous. It's not enough to just say, tried prompt injection X. You need to record the exact prompt used, the model parameters like temperature settings, if controllable, the specific model version being tested, and the full verbatim output received from the LLM. The goal is reproducibility. Someone else should be able to take your notes and repeat the exact same test under the same conditions. The guide refers to minimum reporting requirements, Mindeststand Fordering and Recording, A9, that stress this level of detail. Ensures the findings are verifiable and not just anecdotal. Hashtag 5.4 evaluation, risk assessment, recommendations, and reporting.
All right, the testing is done, the data is gathered. Now for the final phase, making sense of it all and communicating it. The guide seems to stress that the final report really needs to speak to two very different audiences.
Just exactly. The reporting has to bridge the gap between deep technical findings and business impact. So first, you have the management summary, 5.4.1. This needs to be concise, high-level, written for decision makers who might not be deep tech experts. It should cover what was the goal of the test? What's the overall security posture, good, bad, ugly? What were the most critical vulnerabilities found? And crucially, what are the top 2-3 actionable recommendations? Keep it short, clear, and focused on business risk.
And then for the technical teams, the ones who actually need to implement the fixes.
That's the technical report, 5.4.2. This is where you get into the weeds. It needs the detailed methodology used, a thorough description of each vulnerability found, which specific components are affected, and absolutely vital, clear, step-by-step reproduction steps so the developers can see the issue for themselves. It should also include a risk rating for each finding, often using a standard like CVSS, and provide concrete, specific proposals for how to remediate the vulnerability. This technical report usually has an appendix, 5.4.3, containing all the supporting evidence gathered during testing, screenshots, logs, example chat interactions, relevant technical specs. The final deliverable isn't just the report, though. It should include clear, documented recommendations prioritized by risk, and ideally, a suggestion for the timeframe for the next test cycle, reinforcing that this is a continuous process, not a one-off event. #tag deep dive into risk scenarios, Appendix A6.
To really understand the kinds of things these tests are looking for, let's drill down into Appendix A6 of the guide. It provides a detailed catalog of specific risk scenarios unique to LLMs. Let's start with A6.1. Risks inherent to the LLM model itself, regardless of how it's deployed.
Right. These are the baseline vulnerabilities tied to the nature of the models.
And top of the list, unsurprisingly, is A6.1.1, prompt injection, indirect prompt injection.
It's the central risk, really. The goal here is usually to make the LLM bypass its safety guardrails, generate harmful or forbidden content, or perhaps trick it into revealing internal system information, like the specific underlying model name, its system prompt, or maybe even API keys embedded in its configuration. The testing focus, Proofsvorplan, recommended by the guide, is heavily geared towards automated testing, trying out large numbers of different injection techniques and variations to assess the probability of success against the model's defenses.
Next up, a major confidentiality concern. A6.1.2 information leakage.
This is where the model inadvertently reveals sensitive data that it was exposed to during its training. It might have memorized specific personal details, confidential business information, or proprietary code snippets. The testing approach here involves explicitly probing the model with prompts designed to elicit known sensitive information patterns relevant to the organization or common PII formats. You're essentially testing the model's memory for secrets it shouldn't be sharing.
And the one that impacts trust and reliability, a 6.1.3 hallucinations.
When the model competently states things that are factually incorrect, misleading, or just plain made up, it violates the goal of integrity. Testing for this involves not just asking it questions where you know the answer, but also using automated fact-checking against its outputs and probing how it responds when it genuinely doesn't know something. Does it admit ignorance, or does it confabulate confidently?
In the societal dimension, a 6.1.4 bias discrimination.
This is a huge area. Does the model produce outputs that are unfairly biased against certain groups based on attributes like race, gender, religion, etc.? This often stems from biases present in the vast amounts of text it was trained on. Testing here needs to be rigorous. The guide suggests using automated tools designed to detect common biases, but also performing application-specific testing, asking the same questions but varying sensitive attributes in the prompt to see if the model's answers or decisions change in discriminatory ways. Day 6.4 risks related to integration forms. Okay, now let's look at the risks that emerge when the LLM is connected to other systems. The integration risks from section A6.4. This is often where things get really dangerous. Let's focus on a few key examples, starting with the use of tools, Werkzeug, A6.4.11. Right. Giving the LLM the ability to call external tools is powerful, but it's a major risk magnifier. The first risk, A6.4.11.1, is simply that the vulnerabilities are in the tools themselves. The external code the LLM is calling, maybe it's an old API, maybe a script someone wrote quickly, might have standard bugs like not validating inputs correctly. If a user sends a prompt injection to the LLM might interpret that injection and pass the malicious payload as legitimate data to the vulnerable tool. Your LLM just became the vector for exploiting a traditional vulnerability in a connected system.
But what if the tool itself is secure, but the environment it runs in isn't?
That's the next risk. A 6.4.1.4 unnecessary tool permissions. Let's say you give the LLM a tool to check meeting room availability, but the service account or environment where that tool runs has, for some reason, admin privileges on the entire server or access to sensitive databases it doesn't need. Now, if an attacker manages to exploit the LLM or the tool, even slightly, they might gain access via those excessive permissions. The principle of least privilege is absolutely critical for tool integration. An exploit's impact gets massively amplified if the tool has too much power. This violates confidentiality, integrity, and availability, plus data protection rules.
Let's shift to a 6.4.12.3 insufficient isolation. Sandboxing is the main danger. If the environment where the LLM's dynamically generated code runs isn't properly locked down, that code could potentially break out. It might read sensitive files from the host system, write malicious files, probe the internal network, or change system configurations. The sandbox needs to be incredibly robust, treating the LLM-generated code as completely untrusted. And there's also a process risk here, right? 6.4.110.6. No human in the loop for critical actions.
This is a huge safety concern, especially as we move towards more autonomous agents. If the system allows the LLM, or the code it generates, to perform critical, irreversible actions like deleting large amounts of data, initiating financial transactions, controlling physical hardware without requiring confirmation from a human user, you're asking for trouble. A single hallucination by the LLM or one successful prompt injection could autonomously trigger a catastrophic event. For high-stakes actions, you almost always need that human verification step as a safety brake.
Okay, finally, let's revisit A 6.4.14 Retrieval Augmented Generation, RAG. We mentioned data poisoning, but what are the key risks testers look for here?
Two main ones stand out. First, A6.4.14.2 data poisoning. The attacker doesn't target the LLM directly. Instead, they try to insert malicious content into the knowledge sources that the RAG system draws from. Maybe they compromise a document repository or upload a file containing hidden instructions. When the RAG system retrieves this poisoned data to use as context, those hidden instructions act as an indirect prompt injection, manipulating the LLM's output. You have to ensure your RAG data sources are trusted and validated. The second, often missed, risk is A6.4.14.3 insufficient access controls in the retrieval process itself. When the RAG system fetches relevant documents based on the user's query, does it also check if that specific user has permissions to view those documents according to the organization's standard access control policies? If not, the RAG system might retrieve sensitive data, feed it to the LLM, and the LLM then exposes information to a user who should never have seen it. It's a confidentiality breach bypassing normal permissions. Hashtag illustrated damage scenarios.
It's really important to connect these technical vulnerabilities to tangible, real-world harm. Appendix A7 in the guide does exactly this, providing illustrative damage scenarios categorized by impact type, A7.1. Let's look at a few examples from their list, A7.2.
Yeah, grounding it in potential damage makes the risks much clearer. Let's start with the most severe. Dunter 1, physical harm. This scenario imagines a service robot controlled by a cyber-physical LLM agent system. A myth-interpreted instruction, perhaps due to a prompt injection or a hallucination, causes the robot to move erratically or too fast, resulting in physical injury to a nearby person. This underscores that LLM security failures can have kinetic consequences now.
Beyond physical harm, there are unique economic risks too, not just theft.
Absolutely. Consider Netter 12, organizational economic damage. This highlights the denial of wallet attack. Maybe flawed logic in an agent system, or an automated attack exploiting dynamic cloud pricing causes the LLM application to consume cloud resources uncontrollably, making millions of API calls, spinning up expensive GPUs. The result isn't stolen data, but a potentially bankrupting cloud bill. The attacker targets your finances, not just your data.
And the kind of damage that can sink a brand reputation.
That's Enter 23, reputation trust damage. This is the classic scenario where users publicly trick a company's customer service chatbot, using prompt injection, into making outrageous, offensive, legally questionable, or simply false statements. Maybe it guarantees a price the company can't honor, or gives dangerous advice. Screenshots go viral, trust evaporates, and the brand takes a massive hit.
And finally, legal harm that isn't about data breaches or physical damage.
Right. Nanner 26, legal harm, focuses on compliance failures. This scenario involves using an AI system in a regulated domain, finance, healthcare, etc., where specific legal mandates apply or where certain AI uses might even be prohibited. If the deployed LLM system violates these regulations, e.g. a high-risk AI system used without the proper conformity assessment required by the AI Act, the organization could face significant fines and legal sanctions from regulators, even if no actual security incident or data leak occurred. It's purely about failing to meet the legal requirements for deploying AI in that context. #outro.
Wow. Okay. We have covered a huge amount of ground today, really diving deep into these comprehensive guidelines for penetration tests of large language models. We've gone from the foundational concepts, the probabilistic nature, the new vocabulary, all the way through the critical legal prerequisites like the AI Act and GDPR, and into the nitty-gritty of complex integration risks involving RG, tools, and autonomous agent systems. It's a lot to take in, but these guidelines really do provide that essential structured starting point that organizations need. They're critical because they systematically push AI security beyond just basic IT practices. They give you the framework to actually meet those demanding legal compliance standards, proving robustness for the AI Act, demonstrating effective measures for NIS2 and DORA, ensuring GDPR's technical requirements are met.
And crucially, that standardized four-phase process, the analysis, planning, testing, and reporting, brings much-needed structure. It aims to make LLM penetration testing a more repeatable, comparable, and ultimately actionable service. That's vital for security officers justifying budgets and for auditors needing concrete proof of resilience against these unique, non-deterministic threats. I think the single most important takeaway for everyone listening has to be this. Securing LLM applications isn't a one-and-done task. It must be a continuous process. Because these models evolve, because the integrations change constantly, because the hack techniques are developing rapidly, a single test only gives you a snapshot in time. Organizations absolutely need to build this kind of rigorous, structured testing into their ongoing development lifecycle management. You have to keep pace with the changing risks.
That really does bring us to a final, quite challenging thought for you, our listener, to mull over. We've talked about the increasing autonomy of systems like LLM routers and especially agent systems AI that can dynamically choose models, interact with tools, even control physical actions. The question becomes, how far into that decision-making autonomy can we, or even should we, extend human oversight and safety controls before the system becomes so hampered by checks and balances that it loses its utility? Where is that optimal point on the spectrum between maximum usefulness and guaranteed safety? Finding that balance might just be the core security challenge of the AI era.